In this video, we'll begin our discussion of the chain rule in 3-space. So to recall from Calc 1, our chain rule came from this idea, and most Calc 1 teachers will look at this and they're like, okay, how you can think about this is, these can cancel out, getting us back to dy dt. Can't do that, right? It doesn't work that way, but it's easy to think about it that way. Our chain rule, we would always take the derivative with respect to the variable we're thinking of, and then there would be some inside function that we would take the derivative of, and that's what that is. Now, we're going to use this idea to build up a chain rule formula for 3-space. So first thing, we're going to work off this example because it's easier to talk about something. Notice we have some function w. W is built like this, where it's dependent on x and y, but x and y are composed here from t. So a couple things we should note. X and y are intermediate values. So what that means is they're not the value I'm plugging in or the value I'm getting out. It's just going to be a variables that I plug in t, holds the place for something, and then I do something else with it. Okay. With that, t is our independent. Is the independent. That's the one that we'd actually choose and plug in. Then that would give me an x and a y. Then I would use x and y to figure out w. So x and y are kind of the in-between. All right, let's talk about, let's build a formula, and then we'll use the example we'll use the formula with the example. Okay, so notice that as t changes, okay, and we'll call changes for t as delta t, so change in t. As t changes, x and y also change. So x and y respond to the change in t. Respond by changing also. All right? This makes sense. As t changes, x and y will change. Right? Let's write change of x and change of y. That's what those are. So changing also, and both of those changes, x and change in y, cause a change in w, right? And that is delta w. Now, let's make sure you understand what's being said there. If I change t, t affects x and y change, and then that affects w. So there's this like domino effect, right? If t is changed, x and y are changed. If x and y are changed, w are changed. So let's write out an equation that kind of explains this. We'll say the change of w is the amount x changes w. All right, it would be that change plus the amount that y changes it. The amount y changes w. So if we take both of those changes and add them together, that is the total change. All right. The amount changes with y. Let's rewrite this. So delta w. We could write this as the rate of change in x direction right? And then we're going to times that by how much x actually changed. So that is our like slope times the change in x. We can do the same thing here. The rate of change in y direction, right? We'll just leave it there, times delta y. All right, we could start messing with this now. I'm going to rename what's in parentheses. We know what those are. Those are partials. This is the w changed by x times delta x plus, right? And the reason this makes sense is this is 1 unit, right? The rate it changes is 1 unit, and then we got to times it by how many x's we have. So I hope that makes sense where that came from. The next thing is the partial of w, not delta, with respect to y times delta y. All right, now we could take that formula and we could shrink it down. I'm going to divide everything by change of t. All right, just a little bit to write down. All right, you can see it's starting to look like that other chain rule. Now, recall this, the limit, got my L, as change of t approaches 0 of delta A over delta B is change of A, or dA, over dB, right? That's the calculus definition of that. So I'm going to let t, delta t, go to 0. So this should be a B right here. If delta B goes to 0, all right, we get dW dt equals partial of W over partial x, or with respect to x, sorry. And then this just becomes dx dt, regular dx dt. This is partial of W with partial y times dy dt. This right here is our chain rule. One of them. We're going to have two of them. All right, that is our chain rule. So I'm going to take this. I got to shrink this up so we can actually do the problem. So you may need to go separate piece of paper, or maybe you have room. All right, I'm going to shrink that down to there. And then we're going to work the problem right here. All right, it just says if I want to find dw dt, which is what was asked, I have to find each part. So I'm going to find dw dx, right? That's using this, and it's a partial derivative. We get 2x. I do partial w with respect to y is going to be 4y. Dx dt, going to need that. That is 2t. That's just from here. And then dy dt is 4t minus 1. So if I want dw dt, I take 2x times 2t plus 4y times 4t minus 1. Now notice everything doesn't match. I have t's and I have x's and y's, but my derivative only calls for, it's like the function w with respect to t. So it'd be nice if everything was just in terms of t. So I'm going to replace my x with the definition that they gave it above. So it's t squared minus 2, and then times 2t, plus 4 times, okay, y was 2t squared minus t, and then that's going to be times 4t minus 1. That is a great answer. You can multiply that out and simplify it, but it's great the way it stands, the way it is. If you'd like to simplify it down, please do, but that covers the whole chain rule. I won't ask you to derive this for me at any point, but that is the idea of where it comes from. The formula is nice and easy to use. I actually think this chain rule is a bit more straightforward than the Calc 1 chain rule, just due to the inside ordeal. People forget or mess it up.